Hybrid solar PV system complete explanation. A hybrid solar photovoltaic PV system is one of the most advanced and flexible solutions in the world of renewable energy. It combines the best features of both on-grid and off-grid systems, creating a powerful, reliable, and efficient source of electricity. While on-grid systems provide economic benefits through net metering and off-grid systems ensure independence through batteries, hybrid systems merge these strengths by remaining connected to the national grid while also incorporating battery storage for backup and optimization. In simple terms, a hybrid PV system is designed to give users energy independence, reliability during outages, and maximum savings on electricity bills. To appreciate the true value of such a system, one must explore its working principles, major components, benefits, challenges, real-world applications, and its growing role in the global transition towards sustainable energy. The foundation of every hybrid PV system begins with solar panels. These panels, typically made of high-efficiency monocrystalline or polycrystalline silicon, capture sunlight and convert it into direct current DC electricity using the photovoltaic effect. When sunlight strikes the semiconductor's surface, electrons are set into motion, creating a flow of electricity. The amount of power generated depends on the number of panels installed, their efficiency, and the amount of solar radiation received at the location. Just like in on-grid and off-grid systems, the solar panels serve as the clean, renewable, and inexhaustible energy source that drives the entire hybrid system. However, what makes a hybrid system unique is how it manages and distributes this energy between the grid, the home, and the storage batteries. At the center of this management is the hybrid inverter, a sophisticated device that combines the functions of both a grid-tied inverter and an off-grid inverter. A traditional on-grid inverter only converts DC electricity into alternating current AC for household use and grid export, while an off-grid inverter manages batteries and independent power supply. The hybrid inverter does both. It converts DC into AC for immediate use, synchronizes with the grid, charges and discharges batteries intelligently, and decides when to draw power from the solar panels, from the batteries, or from the grid. In many modern hybrid systems, the inverter also has smart features such as Wi-Fi monitoring, time of use management, and programmable energy flows. For example, during the day, the inverter prioritizes using solar energy to run appliances, while excess electricity charges the batteries. At night, the stored energy is used to reduce grid dependence. In case of a blackout, the hybrid inverter switches seamlessly to battery power, providing an uninterrupted supply of electricity. The role of batteries in a hybrid PV system is extremely important. Unlike a pure on-grid system, which has no storage, hybrid systems ensure that solar energy is not wasted and can be stored for later use. Lithium-ion batteries, especially lithium iron phosphate, LiFePO4, are commonly used due to their longer lifespan, higher depth of discharge, and efficiency compared to lead-acid batteries. The size of the battery bank depends on the energy demand and the desired backup time. Some hybrid systems are designed to provide only a few hours of backup for essential loads such as lights, fans, and computers, while others are sized to power entire homes for a full day or more. By storing excess solar energy, batteries reduce reliance on grid electricity at night and provide critical backup during outages, making hybrid systems highly attractive in regions where blackouts are frequent. Another key feature of hybrid solar systems is their interaction with the grid. Hybrid systems allow two-way energy flow during sunny hours. When solar generation exceeds consumption and the batteries are fully charged, the excess electricity is exported to the grid, earning credits or financial compensation through net metering. During periods of high demand or low sunlight, the system can import electricity from the grid. This flexibility ensures that the household or business always has access to sufficient energy while minimizing electricity bills. In addition, many hybrid systems include time of use optimization, where batteries are charged during periods of cheap electricity off-peak hours, and discharged during expensive periods, peak hours, providing further cost savings. Designing a hybrid PV system requires detailed planning as it involves balancing generation, consumption, and storage. The first step is assessing the average daily and monthly electricity usage. Suppose a household consumes 600 kilowatt hours per month, which is about 20 kilowatt hours per day. Based on local sunlight availability, the system designer calculates the required solar capacity. If the location receives an average of 5 sunlight hours per day, a 5 kilowatt solar system would generate about 25 kilowatt hours daily, sufficient to meet the demand with a buffer. The battery bank is then sized depending on how much energy the household wants to store. For instance, if backup for 10 kilowatt hours is required, a lithium-ion battery bank with a usable capacity of around 10 kilowatt hours would be recommended. The inverter must also be carefully selected to handle the peak load. If the household appliances collectively require up to 7 kilowatts when operating simultaneously, the inverter should be rated at least 8 to 9 kilowatts for reliability. Such careful sizing ensures smooth operation and optimum utilization of solar energy. The advantages of hybrid PV systems are significant. First and foremost is reliability. Unlike on-grid systems, which shut down during blackouts, hybrid systems provide uninterrupted electricity by switching to battery power instantly. This makes them especially useful in regions with frequent outages or unstable grids. Second is cost savings. By using solar energy during the day and stored battery energy at night, households can drastically reduce their dependence on grid electricity. Net metering further enhances these savings by providing credits for excess energy exported. Third, hybrid systems provide energy independence. While users remain connected to the grid, they are no longer entirely dependent on it, which provides peace of mind during energy crises. Fourth, they are environmentally friendly, reducing carbon footprints by minimizing fossil fuel consumption. Fifth, hybrid systems offer flexibility. Users can choose how much battery storage they want, which appliances to back up, and even program their inverters to optimize for cost savings or reliability depending on their needs. Finally, hybrid systems are future-proof, as they can integrate with new technologies such as electric vehicle charging, smart home systems, and even community microgrids. Despite these advantages, hybrid solar PV systems also face certain challenges. The most notable limitation is their high initial cost. Adding batteries and hybrid inverters significantly increases the price compared to a simple on-grid system. While lithium-ion batteries are efficient, they remain expensive, and their cost contributes to a higher payback period. Another challenge is battery degradation over time. Even advanced lithium batteries have a finite lifespan, typically around 10 to 15 years, after which they must be replaced. The complexity of hybrid systems also requires skilled installation and maintenance. Without proper design and management, issues such as overcharging, inverter overload, or inefficient energy use can arise. Furthermore, policies around net metering and grid interaction vary from country to country, which can affect the financial benefits. For example, in regions with weak or no net metering policies, exporting energy to the grid may not provide sufficient compensation. Lastly, hybrid systems require space for both solar panels and batteries, which may be a constraint in densely populated urban areas. The real-world applications of hybrid PV systems are expanding rapidly in residential homes across Asia and Africa. Hybrid systems ensure reliable electricity during long power outages while reducing dependence on costly diesel generators. In commercial buildings and offices, hybrid systems cut down electricity bills significantly while providing backup for critical operations like servers and computers. Hospitals and health clinics, especially in developing countries, rely on hybrid solar to maintain refrigeration for vaccines and uninterrupted operation of medical equipment. Educational institutions use hybrid systems to keep classrooms lit and powered during blackouts, ensuring uninterrupted learning. In the agricultural sector, farmers use hybrid solar to run irrigation pumps and cold storage facilities while having backup power for essential equipment. Even in industrial sectors, hybrid solar is being used to stabilize energy costs and ensure power reliability. Globally, hybrid systems are also supporting the growth of electric mobility, as they allow households to charge electric vehicles using solar energy during the day and stored energy at night. Looking to the future, hybrid solar PV systems are expected to play an even more vital role in the renewable energy landscape. Battery technology continues to improve. With upcoming solid-state batteries promising higher energy density, faster charging, and longer lifespans. As battery costs decline, hybrid systems will become increasingly affordable and mainstream. Smart Energy Management System, powered by artificial intelligence AI and the Internet of Things IoT, are enabling hybrid inverters to make intelligent decisions about when to charge, discharge, or export energy. This will optimize costs and efficiency further. With the growth of decentralized energy systems, hybrid PV setups can also be integrated into microgrids where communities generate, store, and share renewable electricity independently from the national grid. Hybrid systems will also support the transition toward electrification of transport, allowing households to charge electric cars entirely from renewable sources. Governments around the world are increasingly recognizing the value of hybrid systems in achieving energy security and climate goals, and supportive policies are accelerating their adoption. In conclusion, a hybrid solar PV system is the perfect balance between on-grid and off-grid solutions, combining the cost-effectiveness of grid connectivity with the reliability of battery backup. By capturing solar energy, optimizing its use through smart inverters, and storing it in batteries, hybrid systems empower households, businesses, and institutions with clean, reliable, and affordable electricity. While challenges such as high costs and battery replacement exists, rapid technological advancements are steadily overcoming them. The story of hybrid solar is one of innovation and resilience, providing light during blackouts, reducing energy costs, powering critical services, and contributing to a sustainable future as the world moves toward greater energy independence and decarbonization. Hybrid solar PV systems stand out as a versatile and powerful solution that will shape the energy landscape for generations to come. Subscribe my YouTube channel for upcoming new videos.